Science and Gravity Initiative, who will tell us about the scattering map for horizon regular solutions of the linear wave equation on Schwarzschild.
Thank you, Rita, and thanks to the organizers for inviting me to give this talk. So I will be telling you about the image of the scattering map for horizon regular solutions to the linear wave equation on Schwarzschild. So I will start by describing the problem. So we are revisiting the scattering theory for the linear scalar wave equation on Schwarzschild. So this is the Schwarzschild metric and the familiar Boyer-Lindquist coordinates. I'm going to denote surfaces of constant t by sigma t, but the surface t equals 0 will be denoted by just sigma. And I will also be using double null coordinates. So if I define u and v as such, using the tortoise coordinate, then I can use the coordinate system u, v, theta, phi to write the metric in a double null form. Okay, so in order for a scattering theory to lead to an isomorphism between a space of Cauchy data sets and a space of scattering data, we need to have a collection of conservation laws that allow us to control the solution in both the forwards and the backwards directions of evolution. And then those conservation laws define determine what the scattering map is. So in the case of Schwarzschild, we have time translation isometry. And that, as we all know, that gives us the familiar energy conservation law, which in turn implies the existence of a Hilbert space isomorphism. So I will denote this isomorphism by the maps f plus t and b plus t. And it's an isomorphism between E sigma t and the direct sum of EH plus t and E scribe plus t. So E sigma t is simply the space of Cauchy data for which the flux of the conserved energy is finite. So T is the energy momentum tensor of the solution to the wave equation. And then EH plus T, E scribe plus T are simply defined via the L2 norm of the null derivative on H plus and scribe plus respectively. Okay, so I'm just going to briefly describe what F plus T and B plus T are. So we're giving Cauchy data that lies in E sigma T, and then F plus T defines the trace of the resulting solution to the wave equation at H plus and scribe plus. And those traces always exist if your data is in the initial space E sigma T, and they belong in EH plus T and E scribe plus T respectively. So the map B plus T is the backward scattering map. It inverts F plus T. So if we're given any element of EH plus T and any element of E scribe plus T, then B plus T gives us a solution that achieves CH plus and C scribe plus as the traces at the horizon at null infinity respectively. And it's the unique solution that does so. And then this solution in turn will induce Cauchy data on T equals 0, which belongs in E sigma T. Okay, so I've just taken a small selection of previous works that are directly relevant to the problem where we talk about backward scattering and the scalar linear wave equation. But if I want to expand the list to include other equations of relevance, then it will become much longer. So I apologize if I left out anybody. And please let me know if I should include more names. So Dimock and Kay solved the problem via Cook's method. And as far as I understand, this is the earliest work on scattering on Schwarzschild. Then Bachelot proves asymptotic completeness for the wave equation on Schwarzschild. Batskin and Wang, they studied the asymptotics of the radiation fields and their relation to the asymptotics on the Cauchy surface. And then we have the works of Defremos, Rodniansky, Schlappen-Rosman, and Defremos, Schlappen-Rosman. So this paper actually appeared before this paper, but I think the publication dates. So this paper was published later, I think, than this one. So in this 2018 paper, a scattering theory for the wave equation on Kerr spacetimes is constructed, solving the scattering problem. And in particular, certain properties of solutions constructed via backward scattering are studied, and they're of immediate relevance to what I'm going to be talking about. So I will describe the results in question a bit later. Okay, so what I'm concerned with today is the local energy of solutions to the wave equation on Schwarzschild near the event horizon. So this, the local energy cannot be adequately described using the coordinates little u and little v alone. We cannot use Eddington sign coordinates because they degenerate at h plus. So one thing we can do is we can use classical coordinates because they allow us to extend the Schwarzschild spacetime into the black hole region and the white hole region, etc. And these classical coordinates are defined as such, capital U and capital V. And the relationship between U and V, between the classical coordinates and Boyer-Linguist coordinates can be summarized by this relation where omega squared is 1 minus 2 over r. This is not the only way to describe the local energy, of course. So if I'm only concerned with local energy near the event horizon to the future of some finite little v, then I can use the coordinate system v, r, theta t. And this would actually be a better choice for that particular problem. And in particular, if I want to measure the local energy in a way that's compatible with decay, which is measured via t, then in particular, the transverse null derivative can be written as omega minus 2 d by du. So that would give us a regular derivative operator at h plus. I emphasize u and v because I want to look at both h plus, h minus. But they're obviously not very good as you go to t goes to infinity. Okay, so the central problem that we have here is that this conserved energy does not control the local energy at the horizon. So if we look at the flux of the partial t energy, the conserved energy, on a fixed v slice intersecting the horizon, and we look at the integral near the horizon, then we see that we have the flux of du phi squared in the measure du d vol s2. But the local energy is measured in terms of the integral of omega minus 2 du phi squared in the measure du d vol s2. So having this as a finite energy does not allow us to control this local energy. So what that means is that solutions arising via b plus t can be singular at h plus. Now, to prove that there are actually solutions which are finite energy and are singular at h plus, came through these two papers. So, sorry. Yeah. So in the paper where the scattering theory for the wave equation on curve was established, there was also a little theorem at the very end, which said that for any p greater than 2, if we prescribe as scattering data 0 at sky plus, and then a radiation field that settles down to a pure tail along h plus as you go towards the limit of v going to infinity, then the resulting solution, which is of finite partial t energy, has infinite local energy at the event horizon. And then an analogous result was proven with h plus and sky plus switching places. So that should say for sufficiently large p. We can find c sky plus, which is like a polynomial tail as u goes to infinity, such that if we prescribe as scattering data this c sky plus and 0 at the event horizon, then the resulting solution, which is of finite partial t energy, will also have infinite local energy at the event horizon. Okay, so to get an idea of what kind of obstruction can we face if we try to construct a scattering theory that does control the local energy at the event horizon, then we look at how the wave equation controls that transverse null derivative. And what we get is something that looks like an ODE of exponential type, in the sense that we have this term here. And this term actually distinguishes the direction of evolution in time. So if you're evolving in the forwards direction, then this sign is helpful, and we can easily control the transverse null derivative near the event horizon, provided that it is bounded in the initial data, in the appropriate node, in the L2 node. But if we are to try to do that in the backwards direction of evolution in time, then this sign works against us. So this 2m over r squared is like 1 over 4m near the event horizon. And what that tells us is that if we are to try to close an estimate via, say, Grunwald, then what we need is exponentially decaying data. And then it's unclear if we can close such an estimate for other types of scattering data. Okay, so we sort of have two problems to consider. First of all, if we've seen that for certain radiation fields at H plus, if we pair that with 0 at Scri plus, we get a solution that has infinite local energy. But what if there is some other non-trivial pairing that gives us bounded local energy? So does there exist such a pairing? So that's the first question. It's a question of existence. And then the next question is, suppose we found one. Is there another? So that, in a sense, is a question of uniqueness. But we sort of know already by looking at the equation that if we are to perturb the radiation fields by something that decays exponentially at the appropriate rate, then we'll still have a solution of finite local energy. So it's not that we should have uniqueness, but what kind of class of perturbations are we allowed to have in this case? So I'm going to address the second question first and then turn to existence later. So I'm going to formulate this question and give it the name rigidity of asymptotics. Okay, so the idea is this. If we have two solutions, V1 and V2, arising from scattering data, which are identical at the event horizon, what can we say about radiation field of the difference at Scri plus? And then similarly, we can ask the same question with H plus and C or Scri plus switched. So if we have two solutions which are both regular at H plus, they arise from scattering data that are identical at Scri plus, then what constraints apply to the difference or to the radiation field of the difference at H plus? Okay, so based on that ODE, I already said that we should expect to be able to perturb the radiation field by something that decays exponentially at a rate. And so I'm going to examine these two claims that if we have a regular finite partial T energy solution which has no radiation at H plus, then the radiation field at Scri plus should decay exponentially in the sense that e to the u over the 4m d upc Scri plus, that is in L2. And then the analogous formulation at H plus will be that if you have a solution which is regular at H plus, finite partial T energy and has no radiation outgoing at Scri plus, then e to the v over 4m dvpc H plus will be in L2. So I'm going to examine these two claims. Okay, so I'm going to do this at first instance by decomposing a solution to the wave equation into its spherical harmonic modes. I'm going to analyze L modes separately. Okay, so this claim that I just formulated about rigidity of asymptotics is mostly false. So that's the result that's the first result I'm going to present. It's mostly false, but it's not entirely false. It holds in an important way. So when we restrict attention to solutions of fixed L, then if the radiation field vanishes at H plus, the radiation field at Scri plus will decay exponentially. So statement one holds for fixed L or finitely many L. But if then I allow C to be supported on unbounded L, then actually statement one becomes false. So it's no longer the case that the radiation field should decay exponentially at Scri plus. And finally, for statement two, for any L, there are solutions which are regular at H plus, have vanishing radiation at the Scri plus, and are polynomially decaying at H plus. So statement two is false. Okay, so I'm gonna talk about the proof now. So the ingredient, we have 3 ingredients to the proof. First, we use the analyticity properties of the scattering matrix elements in frequency space. So the proof is entirely in frequency space. And we also use high omega fixed L and high L fixed omega asymptotics of the scattering matrix elements. And we combine these two, and then we apply Paley-Wiener theory. And this is just the theory that tells you the connection between exponential decay in the time domain and holomorphy and integrability in frequency domain. Okay, so we already are working with the equations for fixed L, and now we take the Fourier transform. Now my convention is the physicist's convention. So, So to go from frequency side to the time domain, you have to multiply by e to the minus it omega. Okay, so for this ODE, we define the so-called just solutions, and these are solutions that are normalized at singular points of the ODE. So we have U horizon, which is purely outgoing at the event horizon, whereas R star goes to minus infinity, and then we have U infinity, which is purely outgoing at R star goes to infinity. And then U horizon and U inf, they're different solutions as long as their Vronsky is non-zero, and I'll talk about that in a bit. But out of U horizon, I can create another solution, which I call U horizon bar. This is nothing but U horizon evaluated at minus omega. So the bar refers to reversing the sign of omega rather than complex conjugate as far as the just solutions are concerned. So I have 4 solutions. I have U horizon, U inf, U horizon bar, and U inf bar. So I define the scattering matrix elements as a sort of transition matrix between bases U inf U horizon and U inf bar U horizon bar. And I should already note that T bar is equal to T, but I'll show you why that is a bit later. Okay, so the analyticity properties of the scattering matrix elements I'm going to derive from this theorem, which was proven by Bachelot and Motte-Bachelot in 1993. So for any fixed L and any fixed R star, U horizon is analytic in the region of the complex plane that is not on the negative imaginary axis below 1/4m. So that is, let's say this is 1/4m, and then we exclude just this part. That's U horizon. And then for U infinity, the exclusion area extends all the way to 0 frequency. Now this says for fixed R star, but that's enough for us because we are evaluating Vronskians and we're using those as our benchmark for analyticity as we need it. So T is 2I omega over the Vronskian of U horizon U infinity, and so is T tilde. That happens to be the case on Schwarzschild, but on Kerr, that's not the case. And then we have 2 reflection coefficients, one that's associated with the horizon, one associated with infinity. So R is the Vronskian of U horizon U infinity bar divided by the Vronskian of U horizon U infinity. Now tilde is the Vronskian of U horizon bar and U infinity divided by the Vronskian of U horizon U infinity. So that will be reflected in their analyticity properties. So what that means for us is that the reflection coefficient has this branch cut which extends to omega equals 0, and then R tilde will also have this branch cut, but also will have a pole at 1/4m, and then it will have a sequence of poles at n/4m. And then finally, we have R, which is associated with infinity. And this one just has a branch cut all over the imaginary line. We will not need the full complex plane, and a lot of these properties can be derived by older methods when applied to scattering for Schrodinger. But I think this is the most general result that I found. Okay, so we have that. And now we look at the Fourier transform of the radiation fields. They give us the fixed frequency radiation fields, which I will denote by A. So in the relationship between the fixed frequency radiation fields is given as such. So knowing, for example, H minus, H prime minus, we just multiply by these frequency coefficients, and then we get H plus, etc. And these two are obtained from these two by time reversal, which takes omega to minus omega. Okay, so I'm gonna start with the case when you have no radiation at the event horizon, at the future event horizon. So let's set CH plus to be 0. Then we will have by this relation here that omega AH minus is equal to omega T minus omega A scribe plus. Now I should emphasize that it's I'm using the notation omega H minus to denote the Fourier transform of the radiation field at say H minus, because that quantity belongs in L2, so it makes sense to talk about this Fourier transform. So I'm not claiming that H minus by itself is a Fourier transform of anything. Yeah. Okay, so now we look at the asymptotics of T for fixed L as omega goes to infinity, and we find that T, the norm of T approaches unity for large frequency. This is to be expected. If you think about it in terms of barrier scattering, then for large, if the energy is larger than the peak of the potential, then most of the signal will go through. And this holds not just for real frequency, but also for imaginary frequency. Now I emphasize that because of, so I started from this, convention for the Fourier transform. So as far as exponential decay is concerned, what we're looking for is holomorphy below the real line. But notice that the relation involves T minus omega. So that means we're talking about the analyticity properties of T above the real line. So there's no QNMs or anything like that. Okay, so we assume regularity at H plus, and that implies that CH minus satisfies this estimate. It's e to the u over 2 du CH minus, that's in L2. Okay, now we apply Paley-Wiener theory. So omega H minus is the boundary value of a function that's homomorphic in the strip where imaginary part of omega is between -1/2 and 0. And the supremum of the L2 norm over horizontal lines, the supremum taken over eta between 0 and 1/2, that is also finite. Okay, so we have this property for AH minus, and because omega A scribe plus is in L2 itself, then that implies that T inverse omega AH minus is in L2 by the relation. And so in reality, that's enough to conclude exponential decay, because the L2 norm on horizontal lines, it's log convex. So if you prove it to be bounded here and bounded there, then we can already conclude by Paley-Wiener theory. So that implies that e to the u over 2. I skipped something. I've set 2m to be 1 at some point. Yeah, I think after this slide, 2m is 1. Sorry about that. So e to the u over 2 du c scribe plus, that is in L2. So we have statement 1. Okay, so now I'm gonna disprove statement 2. So all I need is a counterexample. So I'm gonna take omega h plus to be this function. Now the point is the following. I need a function which is holomorphic of the real line, but not integrable on horizontal lines, not in L2. So that means you don't have exponential decay, or like the example that you started from does not have exponential decay. But actually, we can see directly that it's polynomially decaying when measured in L2. So if you are to evaluate this norm, then every power of v will correspond to differentiation by omega, and there will be one term that that comes from differentiating cosine epsilon omega squared that adds powers of omega, prevents integrability. So we can do this for any alpha and take n to be greater than alpha plus half. Okay, but the point is that cosine epsilon omega squared of the real line, it produces exponential growth. But if we make epsilon small enough, then when we multiply by r tilde, we will get something that's integrable. And it's integrable in the entire strip, and therefore we have regularity. So r tilde decays exponentially. That's why I said that we have exponential growth, but not too much. It's because r tilde has exponential decay for fixed L as omega goes to infinity. So this is the same story with barrier scattering. When omega is very high, there's no reflected signal. So it's not very hard to prove that r tilde is bounded above by e to the minus 2 pi omega. We can actually remove the delta, but we need a little bit of work because delta equals 0 corresponds to a pole of the Jost solutions, and that's another story. But we do not need the sharp rate. Okay, so we choose epsilon small enough so that e to the u over 2 du ch minus. We can show that this is an L2 for that example. And then just having this plus the fact that the solution has finite partial T energy, this is sufficient to show that the solution is regular. Sorry, the solution is regular at H plus. So what I'm saying is that if you have here that e to the u over 2 du ch minus, that is in L2, even if you do not have that property along H plus towards the bifurcation sphere, you can do an estimate using the coordinates capital U, little v. And so you only need this and finite partial T energy to prove that the transverse null derivative is in L2. Okay, so this deals with statement 2. We've shown that statement 2 is false. Okay, so the most difficult part of that result is showing that when you have vanishing radiation at H plus but unbounded support in L, you can have radiation fields that decay slower than that rate, e to the u over 4n. So in this case, I show that when you fix the imaginary part of the frequency to be 1/2, and you take L to be sufficiently large, so for some constant, if you take L times L plus 1 to be greater than that constant times omega to the 9, then you have super exponential decay for the transmission coefficient. This is a matched asymptotics problem, but the frequency is not real. So that if you know the ingredients involved, the transition points are not on the real axis, and then you have to do a little bit more work. But it's essentially otherwise all identical. And this is far from optimal, but I don't need that. I mean, even that is too strong or too much. I can prove the result with this. Okay, so it's the same story as with statement 2. So because the transmission coefficient decays, we can pack on a lot of energy and still have regularity at the event horizon. So the idea is this. Let's take a scribe plus to be this function. 1 over L plus 1 to the 3 over 2 times e to the minus cos omega times cosine epsilon L omega. So for any L, This is in L2, and actually the resulting solution for fixed L is exponentially decaying. But because of this cosine epsilon L omega, when you move omega of the real line, then you get growth. And you don't have to see that this radiation field is not integrable on horizontal lines and frequency domain. You can just directly see that looking at this norm, it's the same story. Powers of u correspond to differentiating in omega, which gives us powers of L, which makes it unintegrable. So this is finite energy, but it has this polynomial blow-up. Okay, so the second part of the proof just involves proving some of the familiar properties that we expect from the radiation field at H minus, so that we take the L2 norm of CH minus, and we show that because T decays so rapidly, you will still have a bounded quantity. So this part is slightly technical, but the idea is that you split the sum in L between large L and low L. And for large L, you rely on decay from the transmission coefficient. And then for low L, you rely on the fact that e to the minus twice cosh n dominates any growth that you might get from the low L modes. So as a result, we see that even when we move the radiation field in frequency space of the real axis all the way to minus imaginary part minus 1/2, we still are in L2. So we have regularity at H minus. Any questions? All right, so this is the end of the proof of theorem 1. Now I turn to the question of existence. So if I'm given a radiation field at Chi plus, which is in the finite energy space, can I pair it with something at H plus, which is also finite energy, which such that the solution is regular? And then I can ask the same question with something given at H plus. So, okay, so now I'm gonna distinguish between sigma and sigma bar. So sigma includes the bifurcation sphere. No, sorry, sigma does not include the bifurcation sphere, and sigma bar does include the bifurcation sphere. Because now the norm on Cauchy data will involve H1. So if you don't have support at B, then in the closure, you don't have support at B. So we need to make that distinction. Okay, so just some definitions. So I'm going to define E sigma n and E sigma bar n to be the completion of smooth compactly supported data under the following norms. So the norms are simply H1 on the initial value and L2 on the time derivative, but that's it. And then I take E sigma n L to be the projection of the space onto the span of YLM for a fixed L. Okay, and now I'm gonna define norms on H plus. So I'm gonna address the question first when we're given something at H plus and we want to pair with something at Chi plus. So the H plus norm is basically the H1 norm on R for V greater than some finite V. And then for negative V, say, like near the bifurcation sphere, we just encode the fact that the derivative is regular. That's the definition. And then there's a simplification of that at H plus bar here just is H plus and the bifurcation sphere. This is just because we need to worry a little bit about the behavior of C at the bifurcation sphere, but it's just a technical modification. Okay, so I'm going to define one more space, which is E Chi plus exponential for fixed L. And this is the space of radiation fields at Chi plus, which are finite energy, but which also decay exponentially as U goes to infinity. Okay, so the second result I'm going to talk about is that we have Hilbert space isomorphisms between E sigma n for spherical symmetry and EH plus n for L equals 0, direct sum E Chi plus exponential L equals 0. So we have f plus n and b plus n, and their inverses to one another. And then we have the same result with sigma replaced by sigma bar and h plus replaced by h plus bar. So I should describe what that map means. Okay, so in spherical symmetry, we are somewhat fortunate that there's some simplifications that allow us to close the argument relatively quickly. So the main ingredient in proving theorem 2 are spherically symmetric solutions with no incoming radiation from H minus. Okay, so the idea is that we have that A scribe plus times omega is omega r tilde minus omega over T minus omega A H plus under the condition that AH minus equals 0. So provided you have this, you can show this. Now, T is like omega as omega goes to 0. So omega over T is bounded, which means as long as AH plus is in L2, then we will have omega A scribe plus is in L2. And once we have that, then we actually have found a radiation field of finite energy, which we can pair with AH plus and produce a solution. And that solution will be, by construction, 0 at H minus. Okay. So let's first talk about the forwards map. So for Cauchy data in E sigma n L equals 0, we have that CH plus is in H1. So this is the space where you have no support at the bifurcation sphere. So this is CH plus is in H1. And so as I said, for L equals 0, omega times T inverse is bounded near omega equals 0. So I can take the inverse Fourier transform of this quantity over there and just take its antiderivative, and I'll define that as my radiation field at scribe plus. It's some at this point, it's some function. So first, I'm going to take CH plus and then pair it with F scribe plus CH plus. And that pairing will give me a solution which has no radiation at H minus and is finite energy, which means it's regular at the event horizon. So now I look at C minus C1, where C is the solution that arises from the original Cauchy data that I had. So that is also regular at H plus, but it has no radiation at H plus because C1 was constructed so that it has identical radiation to C. So by theorem 1, the radiation field of the difference, C minus C1, that is in E scribe plus exponential. So what I just said is that any solution in spherical symmetry that is equal to one solution which has no radiation at no incoming radiation from H minus, so we have 0, plus a solution which has no radiation at H plus. So we have 0 here, and we have C tilde scribe plus. So that's the content of the theorem. So I've just described the forwards direction, but backwards direction is similar. I just used the same construction of this solution with no incoming radiation from H minus. So in the backwards direction, we are given CH plus. So I construct this solution with no incoming radiation from H minus, and then I construct another solution from this field that I'm already given, which is in E scribe plus exponential. So I have these two solutions, and I add them up, and I get a solution which is regular at H plus and is finite partiality, has finite partiality energy. So that gives us the backwards direction, and then we have an isomorphism. Okay, so that works for L equals 0, but for L not equal to 0, we have a problem, because now the transmission coefficient vanishes to higher order at 0 frequency. So we cannot repeat the same construction. We can construct solutions using this method if we are given that CH plus is in the intersection of EH plus T and the space H dot minus L. The idea is simple. I just want to consider spaces where I take H plus and divide by T, and I still get something that's in L2, that's integrable. So this is omega to the L plus 1, and this is omega, so I have to worry about the power of omega to the minus L. So if H plus is in H dot minus L, we can carry out the construction as before. But so I cannot quite complete that to an isomorphism, and the reason is that I don't know what kind of Cauchy data would give rise to data which is in H dot minus L. So if I'm given CH plus in this space, then I can construct one solution which is regular and attains the data at H plus, but that solution is not unique. However, the lack of uniqueness is only up to perturbations that decay exponentially at a rate, e to the minus T over 4m. Okay. So in the absence of other ideas, I propose the following, that we make use of the one isometry that we haven't effectively used in scattering yet, which is time reversal isometry. So the idea is as follows. We have that the space of initial data is itself a direct sum of two spaces, H1 and L2. We can study scattering on each one of those factors separately, and then take the direct sum of the resulting maps, and then that identifies the space of radiation fields for which it's possible to pair with something at Scri plus. So why is it useful to split into H1 and L2? It's because solutions arising from H1 and 0, they're time symmetric. And then solutions arising from 0 and L2, they're time antisymmetric, which means the whole solution is determined by one radiation field. So we can understand all the low frequency obstructions and the high frequency obstructions to the existence of a solution. Okay, so let's take C to be in H1. Then we take the solution that arises from C and 0 as the initial data. And then, as before, we have the following relation for A Scri plus, only we replace AH minus by AH plus at minus omega. And this is because of time symmetry. Okay, so what we already have that C is finite partial T energy and is regular, which means what this gives us is a restriction on AH plus. Okay, so the restriction is written in terms of R tilde. Now T, the only problem that comes from T is the vanishing of T to order L plus 1 at omega equals 0. Now R tilde in norm is 1 plus omega to the 2 L plus 2. But we cannot use this. We have to take into account the phase of R tilde. And so that phase, we can expect it to be polyhomogeneous. So we can expect to be able to expand it in powers of omega and powers of log omega. And so the idea is to first make this assumption, which is that I can always decompose R tilde omega and L into two functions. So there's omega L of omega, which contains all the lower order components of the phase. And then whatever that remains is a correction that does not pose an obstruction. So I'm going to take this as an assumption, but I don't know if this is actually true or not. I think that one can by hand derive that this holds for any L, but I don't know if this has been proven for any L. Okay, but under this assumption, then the criterion is this, that I want omega to the minus L times AH plus WL H plus. So this is H plus at minus omega, H plus at plus omega. So I want this combination to be integrable at omega equals 0. If this is the case, then what I can do, so this arises in forward scattering. If I assume my data to be in H1 and L2, but 0 on the L2 side, then if I have WL as such, then I will have proven that this combination is in L2, including at omega equals 0. Now, the same story plays out if I were to try to do this for anti-symmetric solutions. But instead of H plus at minus omega, I will have minus H plus at minus omega. Otherwise, it's the same story. So then I define two spaces, so EH plus N cosine, EH plus N sine, which is defined to be a space of functions which are of finite energy, regular at the bifurcation sphere, and respect this restriction. So this is the space of radiation fields at H plus that come from evolution from H1 and 0. And then this is the space of radiation fields that arise out of evolution from 0 L2. Okay, so then we do have a Hilbert space isomorphism, which is nothing but the canonical isomorphism that you get from having a map between H1 and E, H plus N cosine, and then L2 and EH plus N sine. So you take the direct sum of these two maps, and then you get this map. And what that tells us is that CH plus is necessarily in the sum, not the direct sum, of these two spaces. So it's a little bit convoluted, but at least we do have some positive identification of what kind of radiation fields we can have at H plus. So provided that we know this polyhomogeneous expansion of R tilde near omega equals 0, then we can actually identify exactly what the spaces are. So the story that I've just described plays out in terms of what happens at H plus. So what kind of radiation can we have at H plus? And this is useful because once we can identify that a solution that is given radiation field at H plus admits a solution which is regular, then any other solution will be only different by something that is a small correction because it decays exponentially rapidly. If I want to do the same thing, but with radiation fields based at Scri plus, then I can in principle. But there are several problems. The first of which is that this procedure does not really allow us to identify a candidate at Scri plus, which is distinguished in a way that allows us to prescribe this ambiguity that results from only identifying the radiation field at H plus. This becomes a bigger problem when we try to do this based on radiation fields at Scri plus, because now the correction can be large. So we can only say when we can or cannot construct a regular solution out of a given radiation field at Scri plus, but we have no way of identifying the solution to a useful degree of accuracy. So that's one obstruction, but then there's another one which comes from the difference between the analytic properties of R and R tilde. So we are fortunate that R tilde has this gap between the singularities that allows us to prove everything that we've talked about. R tilde has this branch cut across the entire imaginary axis. So any combination of R and T, which will give us a certain radiation field in terms of what we're given at Scri plus, we will have to worry about those branch cuts. So we cannot use some other surrogate elementary functions that allow us to actually describe the resulting spaces explicitly. So if we are to try to do this with radiation fields based at Scri plus. The resulting function space, we can state it formally, but we don't know what it is. Okay, so that is all I wanted to say. So thank you.
Okay, thank you very much, Rita, for the introduction.